Thanks everyone. The title of my talk today is Open Source Tools for Field Data Collection and Analysis at Geoscience Australia. A brief outline of my talk. Firstly, I'll give an overview of Geoscience Australia and what we do at GA, and why we conduct post-disaster damage surveys and field data collection. And then I'll describe two tools that we use at GA for field data collection and analysis that I've worked on. First one is the Rapid Inventory Collection System, or RICS, which collects data, and FIDAT, or the Field Data Analysis Tool, which analyzes the collected data. And then finally, questions. So, Geoscience Australia is a federal government agency.
Sorry, keep going.
Within the Department of Resources, Energy and Tourism. We currently have around 700 employees, and this is our building in Symonston in Canberra. The current focus of GA's role is in three main areas. Firstly, the future energy and resource base of the Australian economy. Secondly, providing geoscience input to a range of environmental issues. And then finally, and that's where I fit in, contributing to community safety through research into natural hazards and the impact on society. Usually after a natural disaster, after most natural disaster, GA sends out a team to that location to conduct a survey of the damage that is caused by that disaster. Why does it do that? Well, it does that to better understand the damage caused by different hazards to different types of buildings. And what are the objectives of that? Well, first of all, we want to know what type of buildings are subjected to what type of natural hazards, and how those buildings were damaged. Now, structural engineers use those two factors to derive a loss and hazard relationship, and that aids in the assessment of risk for future events, for example for emergency planning, adaptation of legacy structures. There are a lot of buildings in Australia that are old that can be retrofitted, and also modifications to building practices, to current building practices, to minimize future losses. I started working on RICS about 3 years ago. It's been used a number of times. So what is it? It's basically a mobile data collection system. It collects geo-tagged imagery and property damage levels, similar to Google Street View. It's utilized for building or infrastructure damage assessment and inventory information collection. So damage as in how the roof was affected or how the walls were affected. Inventory as in what sort of roof does this building have, how many windows does it have, etc. And the system consists of Ethernet cameras, tripods, a GPS receiver, circuitry, and the RICS software. So the image at the top there is the graphical user interface, and the vehicle at the bottom there is the vehicle that we usually use for surveys. So usually, traditionally, and still even today, GA sends out a team of foot surveyors who walk around, take photos of damaged buildings, and then enter data regarding that building. So they make an assessment on the damage and enter that data into a PDA. But there are difficulties with that. First of all, the working conditions can be very difficult. For example, heat or humidity. Also, people tend to clear debris and start repairs to buildings very quickly. As you can see in this photo here, the debris has been cleared, gathered, and also tarpaulins are used to cover damage, as in this case. So you can't really make a fair assessment of the damage to a building. So what are the benefits of rigs? Well, you're basically in a vehicle driving around very quickly, so you can rapidly prioritize worst hit regions. And then you can enhance the detailed PDA field damage assessment that's performed by these foot surveyors. And also you enable key engineering staff to focus on damaged structures as opposed to structures that are not damaged. And obviously, since you're driving around, you can maximize your coverage of a particular region. The hardware setup, rigs can work with up to 4 cameras, and that's restricted by the Ethernet bandwidth. But we usually use 2 cameras, left and right. Those cameras are attached to a tripod, which are mounted on a vehicle using magnets. The circuitry, both Ethernet and power, the cameras are powered by batteries. There's a network switch, obviously a laptop, a GPS receiver, an inverter that powers the laptop and the network switch, and that's connected to the auxiliary power source of the vehicle. The software components, I developed the software in C++ using Microsoft Visual C++ Express. It uses wxWidgets for the graphical user interface. It's open source, provides good documentation, has a fairly large user community, and is cross-platform. The software is multi-threaded, so it uses wxThreads for that. The data that is collected is written into an SQLite database. It also makes use of C++ Boost library, and also to accelerate the JPEG compression. It compresses the images that are collected are compressed in JPEG. It uses the libjpeg turbo library, which is written in assembly. So it was developed by a single engineer, software engineer, using an iterative development process. And each iteration included requirements gathering. So I worked with a field officer and a project manager. They were the users of the software, design of the software, coding, and then testing. And we found that field testing before actual deployment really provided us with very valuable feedback as to how the software would perform in a real-life situation. This is a graphical user interface. It consists of 3 sections. The streamed images are displayed in the top section. The current GPS data is displayed in the middle section. And the bottom section is a text box. That's actually quite unique to this software, where a user can type in a note, or they can use keyboard shortcuts to enter a predefined note, for example, damage to a building, and then that note is time-stamped and geolocated. So as they're driving along, they're looking out, they can type in notes regarding a building. And at the end of the day, those notes can be displayed in a GIS software, and then you get an overview of where the damage has occurred, so you can concentrate on those areas. In terms of the software operation, the camera and network properties can be set from the graphical user interface. The COM port of the GPS receiver can be set manually or automatically. rigs, the way it works, and that really took a lot of thinking as to what makes it easiest to use. It operates in two different modes, test mode and in session mode. In test mode, the images are streamed and displayed, and the GPS data is also displayed, but no database is created, and images are not saved. It's simply there for testing and focusing the cameras. And in session mode, the way it works is that each session of fieldwork is assigned a unique name, usually a geographical location. and the stream images and the GPS data are saved under that session name. Some sample images of the surveys we've done in the past. This is from the Victorian Bushfires, the Kalgoorlie earthquake last year, Christchurch earthquake last year, Brisbane floods earlier this year, and Tropical Cyclone Yasi earlier this year. This is a screenshot of the SQLite database browser, and it shows you what we actually collect and what we actually save. So frame, time, frame number, time, latitude, longitude, the speed of the vehicle, the heading or bearing of the vehicle, the number of satellites that are picked up, the fixed quality of the satellites, and also the camera ID that's associated with this data. The setup is quick and easy. It takes around 5 to 10 minutes just to set the hardware up. And we really also worked on the hardware side of things to make the setting up really easy. And also, we're trying to use off-the-shelf hardware so that anyone can really purchase the hardware and set the system up themselves. And this is a vehicle in action. This is set up inside a vehicle. So recent enhancements, I had some free time earlier this year, so I worked on 2 main issues. One was optimization of the software. The JPEG, through profiling, I realized that the JPEG compression module was actually quite slow. I was using the default that wxWidgets provided. So I replaced that with the libjpeg turbo library that I described before. And the database writes were actually quite slow as well. So I started playing around with that and tweaked it. And the JPEG compression and the database tweaking actually resulted in a 100% speed up, so that was good. Also, we always wanted to release this software as open source. That was our intention from the very beginning. But we were using a DLL that was commercial, and the DLL was the NMIA 183 parser. Now, NMIA 183 are the sentences, the sentence formats that you receive from a GPS receiver. So I rewrote that, and so then it became fully open source. It was released as open source in August, and it's available from Google Codes. Now, why did we release it as open source? Main reason is that we work with our sister organizations in Asia through AusAid, so we transfer our know-how, our technology to them. And we thought the best way to transfer our knowledge to them, or in this case software, is to just release it as open source. Then we would avoid licensing issues and all sorts of other problems. Now, the other tool that I started working on in August, actually, this year, is FDAD, or the Field Data Analysis tool. So basically, we're collecting all this data. We've got the RICS vehicle out. We've got food surveyors. All this data is coming in. How do we process it, and how do we analyze it? We've traditionally been using GIS software from a commercial provider. And firstly, the learning curve is very steep. It's very long. Also, the software is very clunky. So we thought we should just develop our own software so it's easy to learn, it's less clunky, it's quick, and we can modify it any time. So what is FDAD? It's a tool used by structural engineers to extract information on the nature and severity of damage to a building after a natural disaster. It also allows existing data, for example, building inventory data, to be modified, corrected, or updated. It firstly displays a wide range of data sets. For example, RICS imagery. It may display Google Street View, although there might be licensing issues around that. Aerial imagery, street map, and existing inventory data. So a user or an assessor, by looking at this data, they can infer information from this data. For example, the inventory of a building, the damage sustained by that building, and they will enter that information into a database. Also, the other thing that a user needs to do is, from the aerial imagery, is to draw a polygon around the footprint of a building. And that polygon will firstly give you the area of that building, and that's the sort of information we need to collect, the area of a building. And then the centroid of that building is calculated automatically by the software, and that centroid is attached automatically to the closest RIX image. So now you have a RIX image which you've taken, and that RIX image shows you the building, the front of the building. Also, we need the software to extract the building elevation. That's for our own database. And also to save, all of that information is saved in an Esri shapefile. Esri is a commercial GIS company, and they provide an open, it's a commercial product, but it's open format for storing vector data. Sorry?
Not completely open, their index files aren't completely open.
Right, okay, thanks. Now, I decided to build this software using Python, mainly because it provides very good support for geospatial type work. It uses PyQt, which is Python bindings of the cross-platform toolkit, GUI toolkit Qt. It has an open source license, but it also has commercial licenses too. GDAL, it's a library for reading and writing raster geospatial data formats. And SIP, it's a tool for creating Python bindings for C, C++ libraries. And it's developed by the same company that actually develops PyQt. So this is a screenshot of FEEDAT as it stands today. It's around 20% complete, so it's nowhere near the end. On the right-hand side, it displays the graphical data sources available. In this case, it's an aerial image of Sydney. It's in the ECW format, which is a geospatially tagged format of image. And on the left-hand side, you have a drop-down list and we're called addresses, a tab widget, which I'll describe shortly, and a text box underneath where notes can be entered into. It all relies on what is called a template file. A template file follows a specific format, so the format can't be changed, but these components, field names, attributes of buildings can all be changed, and they are really specified by a structural engineer. It really depends what sort of data they want to pick up from these buildings. And I was thinking of actually showing you slides, but since I've got my laptop here, I'll just show you a demo of what the software does. So this is it. This aerial imagery can be panned, can be zoomed into. So it's got that ability. The resolution is low in this case, so I can't go down to the building footprint level. So what happens is that an assessor or a user of the software is given a particular region to survey or assess. That comes with addresses, building addresses. So that's loaded up, and that's in a shapefile. So that's opened up. In this case, all these addresses are allocated to that user, and these appear here. So the user can actually put the initial there as an assessor. And then the template files are ready. So first of all, a inventory template file, and by reading in the template files, this tab widget is dynamically built. we were thinking initially of hard coding everything, but there might be hundreds of different features, and it could change for different locations in Australia or even overseas, and for different natural hazards. So we thought the best thing to do and the most effective thing to do was to dynamically build this tab widget, depending on our template file. So that was the inventory template file. This is a damage template file, so it just builds up this tab widget. So now we have these drop-down lists, damage, and then this is an inventory for roof types, for example. So that what a user needs to do is they look at a RICS imagery or Google Street imagery before and after, and other sources of information, and then estimate, for example, in this case, the height of the eaves, and then fill that in. And then these buttons here, it's not complete yet, but when you click it, you get a picture of an example image of what an eave is, for example. And then you have the damage tab on the side as well. And same thing, so walls, percentages, and so on. So that's just different screenshots. I should also, of course, show you how the polygon works. So you choose a particular region, double click, and then, for example, that's your, say, your polygon. You double click on the first point you created, and that closes the polygon. And say you've made a mistake, so you can move these points and make your polygon more accurate. And later on, I will add the ability to add more points, etc., and delete points as well. So the beta version of the software is due for release in June next year. Although I'm trying to get out an alpha version in December. It's a bit tight, but see what happens. Thank you.
So we have time for some questions.
Why are you working so hard? There's so much open source spatial software you could use to get a running start at that.
That's true. We have a lot of GIS people at work, and they're very familiar with all sorts of software out there. And their assessment was that it's better for us to build a custom made software in-house, so we could modify it, change it, and really develop it to suit our own needs. So that was their assessment.
But you're spending time figuring out how to draw a polygon. There's got to be better things to do with your time.
Yeah, that might be true. Yeah, that might be true. I mean, that's an assessment that was made by the management. It's, as I said,
like kudos on the vehicle and the data collection.
Sorry?
Kudos on the data collection and the vehicle driving and so on. That's really impressive.
Yeah, oh, thanks.
Is the design of the hardware actually, have you released that as well?
Well, actually, it's all on the website. So it's been released on Google Code, and there's a user manual there, and it does describe how to set up the hardware as well. Yeah.
So is your aim to get the general public to set up instances of these cameras and drive them wherever there's a disaster?
No, not at all.
So it will be all handled by government?
Sorry?
It will all be handled by government?
It's all handled by the government at this stage. And also, as I mentioned before, our hope is that our sister organizations in the Philippines and in Indonesia and Papua New Guinea would pick it up, and they're interested in using it. in order to do their own assessment of damage as well.
There seems to be no more questions, so let's please thank Nariman for his presentation.